It's pretty wild to think that there's an entire world hidden right in front of us. A universe that operates by a completely different set of rules, but it's responsible for some of the most amazing things we see every day. Well, it's real. And today, we're going to take a journey into that world, the world of the very, very small.
All right, to get our heads around this, we're not starting in some futuristic lab. Nope. We're starting with a couple of mysteries. One from the ancient world and one from the natural kingdom.
Okay, check this out. This is the Lycurgus cup. It's a Roman chalice that's over 1,600 years old. Now here's the crazy part. When you shine a light on it from the front, it looks like this calm, kind of murky green. But when you put a light inside it, it glows this fiery, brilliant red. For centuries, nobody had a clue how this was possible.
So, that's the big question, right? How can one object be two completely different colors? Is it some kind of ancient magic, or is there something else going on here? Something the Roman artisans stumbled upon by accident? Just hold that thought for a second.
Now let's jump from ancient Rome to the animal kingdom. We've all seen a gecko, right? Scurrying up a perfectly smooth wall or just hanging out on the ceiling like it's no big deal. They're not using little suction cups, and their feet aren't sticky like tape or glue.
So what's their secret? How in the world do they just defy gravity? Well, it turns out that the answer to the gecko's unbelievable grip and the secret of that color-changing cup, they're exactly the same. The answer to both of these puzzles lies in a world so small, it almost feels like science fiction. It's not magic, it's science. So, welcome to the nanoverse.
To really get a sense of just how small we're talking about, let's try an analogy. Okay, picture a soccer ball. Got it? Now, picture the entire planet Earth. The difference in size between that soccer ball and the Earth is the same as the difference between a single nanometer and that soccer ball. Yeah, we're talking mind-bogglingly small.
If you want the hard numbers, the official nanoscale is anything between 1 and 100 nanometers. To put that in perspective, a single strand of your hair is about 80,000 nanometers wide. So we are dealing with things thousands of times smaller than a human hair.
And that brings us to the official definition. Nanotechnology is simply the science of understanding and, more importantly, controlling matter at this incredibly tiny scale, where at least one part of the material is in that 1 to 100 nanometer zone.
What's so cool is that this isn't some brand new idea. Way back in 1959, the absolute legend, physicist Richard Feynman, gave this famous talk, and he asked this question, basically saying, hey, why can't we just move atoms around and build whatever we want? He was literally dreaming up the entire field of nanotechnology before it even had a name.
So why does this even matter? What's the big deal about making something tiny? Well, here's the kicker. When you get down to the nanoscale, the basic rules of physics and chemistry actually start to change. Materials start to get these weird and wonderful new abilities, almost like superpowers. And really, it all boils down to two main things. First, you get a massive, and I mean massive, increase in surface area compared to volume. And second, the truly bizarre world of quantum mechanics starts to take over. The rules for how electrons zip around an atom actually change, and that can alter everything about a material. Its color, how well it conducts electricity, you name it. We call these quantum effects.
Let's break down that first one, surface area. So imagine you've got this solid block of stuff, right? A 1-meter cube. It has a certain amount of volume and a certain amount of surface area, basically the 6 sides of the cube that you can touch.
Okay, now, let's slice that cube in half in every direction. You've still got the exact same amount of material. The total volume hasn't changed at all. But by making those cuts, you've created all these new surfaces on the inside. So the total surface area has gone up.
And if you just keep dicing it up into smaller and smaller and smaller pieces, the total volume always stays the same. But that total surface area, it just grows and grows exponentially. The more surface you have, the more atoms are just sitting there on the outside ready to react with the world around them.
And this graph shows it perfectly. As the size of the particle shrinks down into that nano range, the surface area just explodes. It goes through the roof. This is why nanomaterials are so much more chemically reactive. It's kind of like trying to start a fire. A big log is hard to light, but if you turn it into sawdust, it'll blow up in a flash. More surface, more reaction.
And this brings us right back to our magic cup. Scientists discovered it was infused with tiny, tiny nanoparticles of gold and silver. Now, a big chunk of gold is, well, it's gold-colored, but this is where those quantum effects kick in. When you shrink gold down that small, the size of the particle literally changes how its electrons interact with light.
Different sizes absorb and reflect different colors. So those Roman craftsmen had accidentally become masters of quantum physics, creating this color-changing masterpiece without ever knowing why it worked.
So, if we want to make these amazing materials on purpose, how do we actually do it? How do you build things at a scale you can't even see? Well, scientists have two main strategies, and for one of them, they took a hint from the best engineer in the universe, Mother Nature.
Take a look at a lotus leaf. You've probably seen this. Water just beads up and rolls right off, and it takes all the dirt with it. The leaf stays perfectly clean. This lotus effect isn't from some waxy coating. It's because the surface of the leaf is covered in this super intricate pattern of nanoscale bumps. Nature, it turns out, is the original nanotechnologist.
So, inspired by things like that, scientists came up with two main methods. The top-down approach is kind of like being a sculptor. You start with a big block of material, and you just carve or etch or grind it away until you're left with something nano-sized. The bottom-up approach is more like being a mason. You start with the individual atoms and molecules as your bricks, and you assemble them piece by piece into the exact structure you want to build.
So what can we actually build with all this? Let's zoom in on one of the most incredible nanomaterials ever discovered, just to see the mind-blowing potential here. Let's talk about the carbon nanotube.
So on the left here, this is the structure of graphite. You know, the lead in your pencil. It's just flat sheets of carbon atoms in this perfect honeycomb pattern. Now, imagine you could peel off one of those sheets, just a single atom thick. We call that graphene. And then you just roll it up into a perfect, seamless cylinder. That's it. That's a carbon nanotube.
And the properties of this simple little tube are just out of this world. They have unbelievable tensile strength, stronger than steel, but a fraction of the weight. They are phenomenal conductors of both electricity and heat. They're obviously incredibly light. And get this, depending on the exact angle you roll up that sheet, a nanotube can act like a metal or it can act like a semiconductor, the very thing all of our electronics are built on. So from ancient mysteries to modern marvels, it turns out nanotechnology has been here all along. But now, for the very first time, we can actually control it. We are learning to speak the language of atoms. So the real question isn't what can we do anymore, it's what will we do? Now that we have the fundamental building blocks of the universe in our hands, what are we going to create next?